So we're dealing with something called colligative properties. So a colligative property is a property that depends on the concentration of the solute particles, not necessarily their identity. So this gives you some unique properties of water depending upon what you're adding. What ends up happening, depending on the quantity of the particles, you can have freezing point depression or boiling point elevation. So what colligative properties do is they extend the range of water being a liquid. So there's a few things that we're going to look at in terms of this. So if you look at this chart, the regular boiling point and freezing point of water is 0 degrees Celsius and 100. So what's going to happen was when you add a solute particles, you're going to extend that. So instead of 0 degrees Celsius, maybe you have -5 degrees Celsius, and instead of 100, maybe you have 106 degrees Celsius. So it's extending the range. Because we have two different possibilities of boiling or freezing, we have two different equations, but they are calculated the same way. So for boiling point elevation, we have delta TB equal to IMKB. For freezing point depression, we're going to have the delta TF is equal to I lowercase m kf. So TB or TF, this is your change in temperature. So what we're going to be calculating is the deviation from either the boiling point or the melting point, depending upon which equation we're using. So I is the particle quantity. Depending upon the type of particle you have, you're going to have different number of components to it. So that's something we have to take into consideration. M is the molality, which remember is moles per kilogram. And then Kb or Kf is your constant that's going to be provided to you. So particle quantity. So if you have a covalent substance, such as C6H12O6, covalent substances aren't going to break apart when they dissolve into water. It's just going to dissolve. So this would have a particle quantity of 1. But ionic substances, you can have multiple parts. So in NaCl, you're going to have 2 because you have the sodium ion, you have one of those, and the chlorine ion. In the next example, sodium phosphate, you're actually going to have a particle quantity of 4. You have 3 sodiums and 1 phosphate. So what you're looking at is the total quantity that we have of each of them. And then CaCl2 has a particle quantity of 3. So we have the Ca ion and the 2 Cl- ions. So particle quantity, if it's covalent, is 1. If it's ionic, you have to figure out how many ions you have. If you think of this, this is something that is used when you have treatment on the roads for bad weather. They use different types of de-icing agents. One of the most common is NaCl, but they also use CaCl2 because that would be more efficient. But you could potentially use other things. You could use something like sugar if you have an excess of sugar. To de-ice the roads, it would have the same impact. It just you would need more of it because of it would only have 1 particle as opposed to 2 or 3. So in this example, we have glucose, which we're going to say is C6H12O6. It's dissolved in 255 grams of water. What will the boiling point and freezing point of the solution be? Notice how they give you the constants. You don't have to come up with those. Those will always be provided to you. So Kb is for boiling, Kf is for freezing. So the first thing we have to do for both of these problems is calculate the molality of the solution. So we have the mass of glucose in grams and the mass of water in grams. So we have to convert our 45 grams of glucose to moles, which we know how to do from mole conversions. So 1 mole of C6H12 has a molar mass that we can calculate from the periodic table. So we have a molar mass of 180.18. We end up with 0.250 moles of our glucose. Then we just have to convert our grams of water to kilograms. There's 1,000 grams in a kilogram, so we're going to divide that by 1,000. So we're going to end up with 0.255 kilograms so that we can figure out what the molality of our solution is. Just a reminder, sig figs do matter here. We have 3 sig figs in our mass, so our moles has 3 sig figs. We have 3 sig figs in our mass of our water, so we have 3 sig figs. So our answer will have 3 sig figs. So we have 0.980 as our molality. Remember, this is a lowercase m. I write my lowercase m as a script m to make it clear that it's a lowercase m. But also notice it's approximately half the size of my numbers. So we now have our molality. That's the hardest part of these types of problems. So we're going to calculate the boiling point. So we were given Kf. We're going to be calculating the change in temperature, or delta T, for boiling. So we need Im and then Kb. We have m. We just calculate that. I, because we have a covalent substance, is going to be 1. Molality is 0.980. And Kb was given to us as 0.515 degrees Celsius per molal. Sounds kind of funny, but... So this will give us our delta T, our change in temperature. So you should end up with 0.505 degrees Celsius here. Keep in mind that the 1 or the I value doesn't count towards sig figs because that's an exact value. For every particle you have, you're going to get 1 particle. But if it was something like sodium chloride, it would break up into 2. So it would be exactly 2. But the other numbers you're still going to use for sig figs, so you'll end up with 3 sig figs. Now this is not our final answer. This is just the temperature change. So when we boil water and we add a substance, it's going to increase the temperature. So the boiling point of water is 100 degrees exactly. So you could have an infinite number of zeros here because it's exactly 100. So I could keep going. But we're going to add the 0.505 to it, so we'll end up with 100.505 degrees Celsius. So this is my new boiling point of water. So if we went into the lab and did this experiment, we would find that our water would boil slightly above 100 degrees Celsius. The nice thing about these problems is when you calculate one, it's very easy to calculate the other. So we're going to calculate delta TF, which is the change for the freezing point, which is the same equation, except now we're using Kf. So I is still 1, molality stayed the same, and Kf is 1.86 degrees Celsius per molal. Now, comparing this to the last problem, notice how it's having a bigger impact on the freezing side of it than it does on the boiling side. So we should expect a bigger number here. So you end up with 1.82 here. Now, the freezing point of water is 0 degrees Celsius. I know 0 technically has no sig figs here. I get that. But we need to subtract the value we have. What ends up happening is you're going to stick with the sig figs you get from the last part of it. So you're going to end up with negative 1.82 degrees Celsius. Please don't say in the answer, like, this is an impossible sig figs question. I understand 0 has no sig figs. I do. But we still need to do our best with sig figs here. So our answer here is negative 1.82. So there's two differences. We use different constant values, and at the boiling point we're going to add it to it because we're increasing it, the boiling point. For the freezing point, we're lowering it, so we're subtracting. Remember, we're extending the range of a liquid state of matter here. So just while we're here, electrolytes versus non-electrolytes. An electrolyte is a compound that conducts electricity. So most ionic compounds that dissolve are going to be electrolytes. Non-electrolytes would be something like the glucose we were just dealing with in covalent compounds. So in order for electricity to be transferred in water, you need those ions. And just so you know, the human body requires sodium, potassium, and the calcium ions for various bodily functions. Just to kind of reinforce this, I know this was in biology.